Millions of people use this technology every single day, but almost nobody knows how it actually works inside. Think about it. The last thing you did before opening this explainer. Maybe you unlocked your phone with your face, asked a smart speaker for the weather, or just clicked on a recommended movie. We trust this tech with our schedules, our security, literally our entertainment. But, if you look past those sleek screens, it's a completely hidden, invisible world of staggering complexity.
Welcome to This Explainer, the invisible brain decoding artificial intelligence. Today, we're taking a massive journey from the macro all the way down to the micro. We're peeling back the layers of our modern digital world to decode the hidden architecture of AI. Let's map out exactly how the technology that runs our lives actually thinks. Get ready to zoom in.
Part 1. The AI all around us.
Okay, let's dive into this. Look at the surface level, right? Virtual assistants like Siri and Alexa, recommendation systems on Netflix and YouTube, autonomous vehicles, facial recognition like Face ID, search engines, targeted ads. But behind every single one of these icons lies a hidden digital brain. When Netflix serves up a recommendation, it's not just blindly guessing. These systems are running incredibly intense algorithms, processing massive amounts of data in a fraction of a second. It's vast, highly targeted, and entirely invisible to the naked eye. Part 2. Inside the neural network.
So, to really understand how this works, imagine we're zooming deep inside the interface, dropping all the way down to the microscopic level. And when we zoom in far enough, we find the artificial neural network. It's a computational model fundamentally inspired by the biological neural networks of animal brains. Visualize this as a sprawling, glowing web of digital neurons. But instead of organic cells, they're mathematical functions, communicating at absolute lightning speed.
If we create an exploded view of this digital brain, we see that it's highly structured into basically 3 stages. First, information enters through the input layer. That could be your face or a spoken command. Then it dives into the hidden layers. This is the dark, complex depth where the real processing happens, where millions of connections fire simultaneously to interpret the data. And finally, the processed data emerges at the output layer as a final decision, like unlocking your phone.
And this brilliantly illustrates how these systems actually learn to see the world. An artificial neural network doesn't look at a flat picture the way our human eyes do. Instead, textures and outlines are represented by associated weight patterns across multiple nodes. So when it's recognizing your face, it's not looking at a photograph. It's recognizing a highly specific mathematical signature that's been weighted and calculated across those hidden layers. Part 3. The Transformer Breakthrough. Now let's zoom in even further to the specific DNA of today's most advanced systems, like ChatGPT. The true breakthrough is the transformer. This is a deep learning architecture that models sequential data by utilizing a fascinating mathematical mechanism called attention. Before this, getting a machine to generate human-like text was honestly pretty clunky, but the transformer, it finally cracked the code. To see why this was so revolutionary, let's look at older models. They process text sequentially, literally reading word by word. This meant by the time they got to the end of a long paragraph, they'd kind of forgotten the beginning. But transformers process text in parallel. Using that attention mechanism, they look at everything at once, weighing the importance of every single word in a sentence simultaneously. This is exactly what allows modern AI to understand nuance, sarcasm, and complex context without getting lost.
Now, what's really interesting about this slide is the context window. Even with parallel processing, these models have limits. The context window is basically the AI's short-term memory, the limit on the amount of text a model can process at one time. When you're chatting with an AI, this dictates how far back in the conversation it can remember. Exceed that window, and the earliest parts of your conversation just simply vanish from its awareness.
Part 4. Training the Giant. So, how do these massive digital webs actually learn to do all this? AI isn't born smart. It has to go to school. We use supervised learning, where the AI gets clearly labeled examples. Then there's unsupervised learning, where it's forced to find hidden patterns in raw data all on its own. Self-supervised learning lets the model generate its own labels, and reinforcement learning trains it through digital rewards and penalties. It takes millions of adjustments until the network gets it right.
But running these networks requires some serious physical infrastructure. This isn't just floating around in the cloud. Tech giants build massive, specialized hardware, like Google's tensor processing units, or TPUs, just to handle the intense computational demands. We've moved from lines of code on a screen to massive,
warehouse-sized data centers packed with customized heat-generating silicone. And the scale of all this physical infrastructure brings us to a mind-bending reality. Just look at the 2024 United States Data Center Energy Usage Report. The sheer amount of electricity required to power these places and train these neural networks is absolutely staggering. We are literally channeling rivers of electricity just to maintain the digital brains that power our searches, medical research, and entertainment. The physical footprint of this invisible brain is monumental.
Part 5. Real-world impact and imperfections. This immense technology doesn't just sit in a data center, right? It directly rewires society. Medical writing and scholarly content, automated wealth management on Wall Street, cybersecurity intrusion detection, and even content creation in music and Hollywood. Large language models and neural networks are everywhere. The integration is absolute. But we have to look at the cracks in the foundation.
Because these systems are far from perfect. AI is highly vulnerable to concept drift, meaning its accuracy actually degrades as the real world changes. It suffers from dataset bias, mirroring the historical prejudices hidden in the training data. And perhaps most concerning is a troubling lack of interpretability. These things are literal black boxes. Even the human engineers who built them often cannot retrace the AI's billions of weight patterns to figure out why it made a specific choice. So the crucial point is that these theoretical flaws have devastatingly real human consequences. The data confirms that biased facial recognition technology, built on flawed datasets, has been shown to cause racial discrimination in the criminal justice system. When a mathematical weight pattern misidentifies a face, it isn't just a glitch on a screen. It can result in a wrongful arrest. The stakes of this invisible architecture are incredibly high.
As these digital brains grow exponentially larger and consume more of our world's resources, we are left with a critical question. Are we just programming a tool, or are we building something we don't fully control? We've zoomed from the apps on your phone down to the mathematics of the neural network and back out to the energy grids and societal impacts they create. If you enjoyed discovering how this works, subscribe for more amazing technology and science explained.